We are in section 7.2, Trigonometric Integrals. Remember the trigonometric identities from previous math courses. So I've listed them here for you to reference. And we have the reciprocal identities, the double angle identities, Pythagorean identities, half angle identities, sum and difference identities, and the power reducing identities. These at the bottom of page 5 are all identities that you should already know, and if you don't know them yet, then make some flashcards and make sure you have these memorized. So at the top of page 6, we have our first set of differentiable rules for trigonometric functions. So we have the derivative of sine of x is cosine of x, the derivative of tangent of x is secant of x, the derivative of secant of x is secant x tan x, and the derivative of cosine of x is negative sine of x, derivative of cotangent of x is negative cosecant of x, squared of x, and then the derivative of cosecant of x is negative cosecant of x, cotangent of x. These you should know. If you don't, again, make sure you have these memorized. When integrating problems of the form sine to the m power of x, cosine to the nth power of x dx, we generally try to write the integral involving powers of sine and cosine in the form where we have only one sine factor and the remaining of the rest of those in terms of cosine, or only one cosine factor and the remaining part of the expression in terms of sine. We can then use the Pythagorean identity to convert between sine and cosine. So first thing we have here is powers of sine and cosine, and we have, if this is the integral of sine m of x times cosine n of x dx, and if m is odd and n is a real number, and we're just going to go through the different cases to kind of see how this will work. We would have the integral of sine m to the x cosine n of x dx. And it says split off one power of sine x and rewrite the remaining even number of powers of sine x in terms of cosine of x. Use a u substitution with u is equal to cosine of x. So we're going to say let m equal 2k plus 1 since m is odd. And so this is going to be the same thing as the integral of sine squared of x to the kth power times sine of x, and then the cosine we would leave the same, cosine n of x dx. And so this way that we rewrote this in terms of sines is going to be sine 2k plus 1 if you were to use your exponential rules. From here, I'm going to go ahead and use my Pythagorean identity and say that sine squared of x is the same thing as 1 minus cosine squared x, and then this is all raised to the kth power, and then we have sine of x cosine n x dx, and from here we can use u substitution and let u equal cosine of x, and then du would equal negative sine x dx, and then keep going with the problem. Likewise, case 2 would be if n is odd and m is a real number. And so likewise for this case, we're going to let n equal 2k plus 1 since it is odd. And so this time we would have the integral of sine mx cosine nx dx, and this time it's cosine that we're dealing with that is odd, so my sines are going to stay the same, so sine m to the x times, and we have cosine squared x to the kth power times cosine of x dx, which again, using those exponential rules, you would have 2k plus 1, which is equal to n as we defined it. And so from here I'm going to use my Pythagorean identity and rewrite this. We have sine m of x times, and then we have cosine squared, which is the same thing as 1 minus sine squared x to the k times cosine of x dx. And we would let u equal sine x, and du equal cosine of x dx. The next case says if m is greater than or equal to 0 and n is greater than or equal to 0, but both are even, then for this we're going to use half-angle formulas to transform the integrand into a polynomial in cosine 2x and repeat former strategies as needed. So we would use sine squared x is equal to 1/2 times 1 minus cosine 2x, and also cosine squared x is equal to 1/2 times 1 plus cosine of 2x. And it's sometimes useful to use, so we'll say sometimes useful to use our double angle formulas. So when you have 2 sine x cosine x, that's the same thing as sine 2x. So some different things to keep in mind. So we have some examples on the next page that we're going to look at. So the first one says, find the integral of sine to the third x times cosine to the fourth x dx. And since our sine is odd, we're going to go ahead and rewrite that and break off one of the signs and then write the other ones. That would be an even power. And so I'm going to go ahead and say this is equal to the integral of sine x times sine squared x times cosine to the fourth x dx. From here I'm going to use the Pythagorean identity to rewrite the sine squared that we have in terms of cosine squared. And so this will be the integral of sine x. Sine squared x is the same as 1 minus cosine squared x times cosine to the fourth x dx. Now, since I have everything in terms of cosine and just one sine, I'm able to use u substitution and let u equal cosine of x. And then du is going to be negative sine x dx. So using this, I'm going to now have the integral of, and sine of x dx is equal just to that negative. And I'm going to have 1 minus cosine squared, so u squared, times cosine to the fourth, which is u to the fourth, and then du. So distributing through the negative and the u to the fourth, we have the integral of u to the sixth minus u to the fourth du. And this is easy to integrate. We have 1/7 u to the 7th minus 1/5 u to the 5th plus c, since we are dealing with an indefinite integral. And then I need to back sub in cosine of x every time I have a u. I have 1/7 cosine 7th power of x minus 1/5 cosine to the 5th power x plus our c, our constant term. The next example we have is a definite integral, and this one says find the integral from 0 to pi over 2 of sine to the 5th x dx. And since I'm only dealing with sines, I'm going to go ahead and, since it's odd also, and break off one of those signs. So this is going to be the integral from 0 to pi over 2 of sine x times sine to the 4th x dx. And this is the same thing as 0 to pi over 2 of sine x, and this is the same as sine squared x squared dx. And then I'm able to use the Pythagorean identity and rewrite sine squared in terms of cosine. And so we have 1 minus cosine squared x squared dx. And so from here, I can let u equal cosine of x, and then du is going to be negative sine x dx. And so we're going to have the integral of, and it's negative, I'll put the negative out in front, and sine x dx is just du, and then 1 minus u squared squared du. And remember that since we did use u substitution, we do need to change those limits of integration since we are dealing with a definite integral. So we have cosine of pi over 2 and cosine of 0. And cosine of pi over 2 is 0, and cosine of 0 is 1. So we would be integrating from 1 to 0, which we can then rotate. We can flip that since we do have a negative out in front. That would now become positive. So this is going to go from 0 to 1, flipping those limits of integration and also changing that sign. You can FOIL out or multiply out 1 plus u squared squared, and you get 1 minus 2u squared plus u to the 4th du. And you can integrate this in terms of u. So we end up with u minus 2/3 u to the 3rd plus 1 over 5 u to the 5th. And we need to evaluate this from u equals 0 to 1. So we're going to substitute in 1 first. So we have 1 minus 2/3 plus 1/5. And then when we substitute in 0, we do just get 0. From here you can combine these, get a common denominator, and simplify, and you get 8 over 15. So the next example that we have, I'm going to go ahead and circle, and we'll look at that one together in class. The example on the next page says find the integral of sine cubed square root of x divided by the square root of x dx. First thing I notice is that I have that extra square root of x in the denominator there, and I'm going to go ahead and try to rewrite this, and I'm going to let y equal the square root of x. And then dy would equal 1 over 2 square root of x dx, which would allow me to simplify this a little bit and rewrite it. So I'm going to end up with 2, the integral of, and it's going to be sine cubed y and I have 1 over the square root of x dx, which would just be my dy since I have the 2 already in there. And now that I have rewritten this in terms of my angle just being y, it makes all of those properties and identities useful. So from here, it's an odd sign, so I'm able to break off one of these signs and say sine of y times sine squared of y dy. Rewriting the sine squared y in terms of cosine, I'm going to have 2 times the integral of sine y times 1 minus cosine squared y dy. And again, this time I'll let u equal cosine of y, so then du is going to be negative sine y dy. And I'm going to put the negative in front of the 2. So negative 2, the integral of, and I'm going to have 1 minus u squared. And then sine y dy, since I already have the negative in there, would just be du, which integrates really nicely. So we have negative 2 times u minus 1/3 u cubed plus c. I'm going to distribute my negative 2, and then I need to back sub in what u is. Remember, u is just cosine of y, and then we also need to substitute back in and say y is square root of x. So one thing at a time. I have negative 2, and I'm also going to distribute this. I have negative 2 cosine y plus 2/3 cosine cubed y plus c. And then now substituting back in that y is equal to the square root of x, I'm going to have negative 2 cosine square root of x plus 2/3 cosine cubed square root of x plus c. And that would be my final answer. Again, making sure that you rewrite your answers, especially for indefinite integrals, in terms of that original variable that we have, and don't forget your plus c. We have another example below, and this time it says find the integral of cotangent to the fifth theta times sine to the fourth theta d theta. And so this time though, because I was using that Pythagorean identity, it needs to be in terms of sines and cosines, and it's in terms of cotangent and sine. So I'm going to first try to rewrite cotangent in terms of sines and cosines and see if that helps. So doing that, I'm going to have the integral of cosine to the fifth theta over sine to the fifth theta, sine to the fourth theta, d theta. So from here I do realize that it does simplify, and my sines are going to definitely reduce, and I have cosine to the fifth theta over sine of theta, d theta. And so I have a single sine, which is nice, but I need to rewrite my cosines in terms of those even powers so I can use that Pythagorean identity. So I'm going to go ahead and rewrite this as cosine theta times cosine to the fourth theta, which is the same thing as cosine squared theta squared d theta. And then using that Pythagorean identity, I'm going to have the integral of cosine theta times 1 minus sine squared theta squared all over sine of theta d theta. And so from here I'm going to let u equal sine of theta. And then my derivative, my du, would be cosine of theta d theta. So from here I can rewrite this integral as the integral of, it's going to be 1 minus u squared squared all over u, and then du, which you can multiply out the numerator and you end up with 1 minus 2u squared plus u to the fourth all over u du. And then from here we're going to have the integral of, and it's going to be 1 over u minus 2u plus u to the third. And this would be breaking each of these terms up individually and being 1 over u minus 2u squared over u, and then simplifying it, plus u to the fourth over u du. So integrating from here, we have ln of the absolute value of u minus u squared plus 1/4 u to the fourth plus c, since this is an indefinite integral. And remember, our original problem is written in terms of theta, so I do need to back sub in what that was. And u is defined as sine of theta. So this is going to be ln of sine theta minus sine squared theta plus 1/4 sine to the fourth theta plus c. That would be my final answer. There's another example at the bottom that I'm going to go ahead and circle, and we'll look at that one together in class. We can use a similar strategy to evaluate integrals of the form tangent to the nth power x, secant to the nth power of x dx. Since the derivative of tangent of x is equal to secant squared of x, we can separate secant squared of x factors and convert the remaining even powers of secant to an expression involving tangent using the Pythagorean identity. Also, since the derivative of secant of x is equal to secant x tangent x, we can separate a secant x tangent x factor and convert the remaining even powers of tangent to secant. So the first case that we're looking at here is powers of tangent and secant. We have tangent to the nth power of x and secant to the nth power of x dx. And for this, we're going to say our n is even. So we have the integral of tangent m of x secant n of x dx. And since n is even, we're going to split off secant squared x, rewrite the remaining even number of powers of secant of x in terms of tangent of x, and use the u substitution with u equals tangent of x. So since n is even, we'll say n is equal to 2 times k. And so this is going to be equal to the integral of tangent mx, and then secant squared x, and then k dx. And so we're going to factor out one of those secant squared. So it says split off a secant squared x. And so this is now going to be tangent m of x, splitting off one of those secants. We're going to have secant squared x. And then since we took one of those out, the remaining ones will be secant squared x to the k minus 1 dx. Again, since we took off one of those secant squared of x's. From here, I'm able to use the Pythagorean identity to rewrite secant squared of x, the ones that we had multiple, and leave the one secant squared x by itself, and rewrite those in terms of tangent squared x. So this is going to be the same thing as tangent mx, leaving the single secant squared alone, and then rewriting the others as 1 plus tangent squared x to the k minus 1 power dx. From here, we would let u equal tangent of x, and then du would be equal to secant squared x dx. The next case is if n is odd and m is odd. So for this case, we're going to split off a secant of x and a tangent of x. Rewrite the remaining even number powers of tangent of x in terms of secant of x. Use the u substitution with u equals secant of x. So since it is odd, I'm going to go ahead and let m equal 2k plus 1. So the problem, which is the integral of tangent mx secant nx dx. And since I defined m as 2k plus 1, I'm going to break off that. So this is now going to be the integral of tangent of squared of x to the k. And I'm also going to take one of the secants out also. So we're going to have secant to the n minus 1 power of x. So we have removed one of the secants. So we have a secant of x left over. And then m is equal to 2k plus 1. So I have an additional tangent also left over. And then don't forget your dx. And then we're able to rewrite our tangent squared x in terms of secant squared using that Pythagorean identity. So we have the integral of secant squared x minus 1 to the kth power times secant to the n minus 1 x times secant x tangent x dx. So next we would let u equal secant of x and du equal, the derivative would be secant of x tangent of x dx. So right below this we have some examples. The first one says find the integral of tangent squared x secant to the 4th x dx. So for this one we have even powers, and so I am going to think about letting u equal tangent of x, and then the derivative would be secant squared of x, like we saw in the first case right up above. So to do that, I am going to rewrite secant as secant squared times secant squared of x. So this will be the integral of tangent squared x times secant squared x, secant squared x dx. And then rewriting one of these secant squared x's in terms of tangent. So this is now going to be the integral of tangent squared x times 1 plus tangent squared x, secant squared x dx. From here, we're going to use u substitution, like we said, and let u equal tangent of x du is going to be secant squared x dx. So from here, we have the integral of u squared times 1 plus u squared times, and then secant squared x dx is just equal to du. You can distribute through that u squared. So we have u squared plus u to the 4th du. And integrating these, we end up with 1/3 u cubed plus 1/5 u to the 5th. And then plus c, since it is an indefinite integral. And then since our original variable is x, we need to back sub in what u is, and u is tangent of x. So we have 1/3 times tangent cubed of x plus 1/5 times tangent to the 5th x plus c. The next example says find tangent to the 5th of x times secant to the 3rd of x dx. So for this case, we would think about using another u substitution, but this time, since I have tangent is odd and secant is odd, this would be dealing with that second case that we had on the previous page. And so for this, I need to break off a tangent x and a secant of x. So this would now be equal to the integral of tangent to the 4th x, secant squared x, times secant x, tangent x, dx. I can then rewrite my tangent to the 4th x as the integral of tangent squared x squared times secant squared x times secant x tangent x dx. And then tangent squared x using the Pythagorean identity is the same thing as secant squared x minus 1 squared times secant squared x times secant x tangent x dx. So now, since everything's in terms of secants and the derivative of secant, which is going to be secant x tangent x, I'm going to go ahead and use u substitution. Let u equal secant of x. The derivative du would be secant x tangent x dx. So this is now going to become the integral of, we have u squared minus 1 quantity squared times u squared, and then secant x tangent x dx is the same thing as du. So from here we can multiply out u squared minus 1 and then distribute in the u squared that's outside of the parentheses. Multiplying these out, we get u to the 4th minus 2u squared plus 1 times u squared du, and then distributing through that u squared, we get the integral of u to the 6th minus 2u to the 4th plus u squared du. And then from here we are able to integrate, and we get 1 over 7 u to the 7th minus 2 over 5 u to the 5th plus 1/3 u cubed. and this is indefinite, so we are going to put a plus c. From here, we just need to back sub in what u was, and u is secant of x. So our answer is going to be 1/7 secant of x to the 7th power minus 2/5 secant to the 5th power of x plus 1/3 secant cubed x plus c. We have another example right below this that I'm going to go ahead and circle that we'll look at together in class that deals with having a definite integral this time. So right below that it says integrals of the form cotangent m of x times cosecant n of x dx can be found by similar methods because of the Pythagorean identity. Remember that 1 plus cotangent squared x is equal to cosecant squared x. In addition, we are able to use the fundamental theorem of calculus to evaluate definite integrals. So the next example says find the integral from pi over 4 to pi over 2 of cosecant to the 4th x cotangent to the 4th x dx. These are both even powers, and I noticed that if I have cotangent of x as my u, the derivative of that would be cosecant squared x dx. So I'm going to go ahead and rewrite this as the integral from pi over 4 to pi over 2 of cosecant squared x times cosecant squared x times cotangent to 4th x dx. And then I'm going to rewrite one of the cosecant squareds in terms of cotangent. So the integral from pi over 4 to pi over 2 of cosecant squared x times 1 plus cotangent squared x times cotangent to the 4th x dx. And from here, I would let u equal cotangent x. And the derivative of cotangent x is equal to negative cosecant x squared dx. So from here, this is now going to become the integral, and yes, we do need to change those limits of integration, but we will do that momentarily. Let's first do the u substitution. And so my cotangents are all now u, and cosecant squared x dx is equal to du. And I do have a negative sign there, so I'm put the negative out in front, and I have 1 plus u squared times u to the 4th du. Since we are dealing with a definite integral, we do need to change those limits of integration. Since my variable is now in terms of u, and my integrand is in terms of u and not x. So in order to do that, I need to find cotangent of my upper limit of integration, which was pi over 2, and cotangent of my lower limit of integration, which was pi over 4. And so cotangent of pi over 2 is just going to be equal to 0. And cotangent of pi over 4 is just 1, since sine and cosine are the same there. And so I'm going to be integrating from 1 to 0. And again, we can flip those limits of integration since they are written backwards with not the lower one being the smallest number, and switch the sign. So this is now going to be the integral from 0 to 1, and it's now positive. And distributing through u to the 4th, I get u to the 4th plus u to the 6th du. And this is a nice one to integrate. So we have 1/5 u to the 5th plus 1/7 u to the 7th. And evaluating this from u equals 1 to 0. So substituting in 1, we have 1/5 plus 1/7 minus, substituting in 0, our lower limit, we get 0. And common denominator, and combining these, we get 12 over 35. To evaluate the integrals below, we will use the product and sum trigonometric identities. So I have written those down for us. So sine of mx times cosine of nx dx, we're going to rewrite that as 1/2 times sine of mx minus nx plus sine of mx plus nx dx. 2 says that if we have sine of mx, sine of nx dx, so if we have both signs this time, this can be rewritten as 1/2 times the cosine of mx minus nx minus cosine of mx plus nx dx. And the third one is if we have both cosines there, where it's cosine mx, cosine nx dx, and integrating that, we can rewrite it as the integral of 1/2 cosine of mx minus nx plus cosine of mx plus nx dx. So below we have an example that's going to use that. Notice that we are dealing with different angles. It's not just theta, like I stated in those formulas right up above. So we have sine of 2 theta and sine of 6 theta. So for this problem, we are dealing with both sines. Then we're integrating this with respect to theta. So I'm going to go ahead and use the second rule that we have up there. So this is going to be rewritten as 1/2 times, and we have cosine of, and it's mx minus nx. So for us it's theta, so it's going to be 2 theta minus 6 theta minus cosine of, and it's mx plus nx. So again, for us it's theta, so 2 theta plus 6 theta d theta. So this is going to simplify now to 1/2. I'll put that out in front of my integral. The integral of, and we have cosine of -4 theta minus cosine of 8 theta d theta. And so cosine is an even function. So just a little note here about cosine. Cosine is an even function. And so cosine of -4 theta would be identical to cosine of +4 theta. So again, this is going to be 1/2 times the integral of cosine of 4 theta minus cosine of 8 theta d theta. And so integrating, we arrive at 1/2 times 1/4 sine of 4 theta minus 1/8 sine of 8 theta. And this is an indefinite integral, so definitely add a plus c. From here, you can clean this up just a little bit if you wanted to distribute the 1/2, or you can leave it as it is. If you wanted to distribute the 1/2, we would arrive at 1/8 sine of 4 theta minus 1/16 sine of 8 theta plus c.